Let's take a look at this interesting optical phenomenon. Here we have the famous bent straw in a glass. Everybody's done it. Everybody's seen it. Everybody knows it. You've got a straw in a glass, maybe not this straw, but a crazy straw or a Slurpee straw, where you put your pencil in, and it bends. So why does it do this? Well, this has to do with the bending of light, or refraction. All right, to understand what's going on, let's take a bird's eye view of the glass. So let's look down at that pencil in the glass. Here's the pencil. It's surrounded by water. And outside the glass is air, right? So we know that in the water, which is a more dense substance, light's going to be slower than it is in the air. So let's watch what happens. And as we watch this, here's your eye, right, is out here looking at the pencil through the air and the water. All right, so you see that as light leaves the pencil, it bends, since it's moving faster here, it bends away from the normal to get to your eye. And so your eye actually traces these two rays back to see the pencil over here, right? In a different position than it actually is. It's here in the air, it's here in the water, and that's an optical illusion. You could see that again if we watch. As the light leaves the pencil, it refracts or bends and comes towards your eye. And your eye sees these two rays and thinks the pencil's here. Pretty awesome. So here's our next line. You can add this to the equation sheet. But this is Snell's law. So Snell's law allows us to find how much light bends when it passes from one medium to another. So let's just take it for a test drive. So here we have a light ray, wavelength 589 nanometers, traveling through air, strikes a smooth, flat slab of crown glass on an angle of 30 degrees to the normal. Find the index of refraction. So first thing, when we're looking at this, we're going to need to find how much light slows down in crown glass and air. So if you look at Snell's law, it requires we need the index of refraction of both mediums. So I'm going to put the table back from last video. I'm going to put that table back up. Here are the indices of refraction for various substances. So our picture is going to look like this. Light is traveling through air. So we have our interface here. This is air, and this is the crowned glass. Air has an index of refraction. For most problems, it's okay to just use 1. You can see air's index of refraction is extremely small, which means light travels almost as fast in air as it does in the vacuum of deep outer space. Crown glass we find here is 1.52, so light is slower in crown glass. So if we have our incident beam coming in to the interface, I draw the normal line. This is known as our angle of incidence. So this is theta I. Whoop. Okay, so we now think, is light going to bend towards the medium or away from the medium? Well, since it slows down in crown glass, right? Fast to slow towards, right? FST, freaky science teachers. So that's going to be towards the medium. So this is theta R, which is the angle of refraction. So now it's just a plug and chug. So we've got Ni, which is the index of refraction of air, is 1. The angle of incidence is 30 degrees. And that equals 1.52 times the sine of theta. So when I solve this, I get sine of theta R equals 0.329. I forgot to put sine up here in my equation. And I solve for the angle of refraction. So I do the inverse sine of this number, and I get 19.2 degrees, which is indeed, it is indeed less than the angle of incidence, which is what we would expect since it slows down in crown glass. Awesome. So in the next slide, I'm going to leave you in this video with one of my favorite creatures in all of nature, and that is the archer fish, who, through some amazing example of evolution, has evolved to adjust its aim for the indices of refraction of water and air. Enjoy and have fun.
The pitiful beetle is the target of a marksman that stalks the tropics of Asia and Australia. The archer fish. One of the few aquatic predators that can hunt prey outside its element. On average, it grows more than 6 inches long. But it can hit a target over 5 feet away, from tiny bugs to small lizards. It forms a tube with its tongue, then squeezes its gill covers to fire. A jet of water shoots out along the roof of its mouth. By positioning itself directly under its prey, it minimizes the effect of refraction of the water. Anyone who has ever tried to spear a fish knows the surface refracts your aim. But not the archer fish's aim. It can even gauge the weight of the target to calculate how much water to fire. A shot typically packs 10 times the force a bug uses to hold on.
What's even more amazing about the archer fish is that you would think that it would sight itself right under the bug. And the reason you would think it would do that is because the light from the bug would not bend, since the angle would be 0. But in fact, it turns out that most archer fish hits are from an angle. And so you can see what's going to happen. The light from the bug, when it hits the water, bends. The archer fish thinks the bug is here, not here. Yet, research has shown that an archer fish's hit probability is not decreased no matter what the angle is. In other words, it has the same hit probability here as it does at an extreme angle. So for somewhat reason, the fish is able to account for physics. So if fish can do physics, so can you. Go get them.